Uh, now, now coming to methods used to improve real-time object detection based on YOLOv8. So we'll see the what are the methods we applied in improve real-time object detection method based on YOLOv8. So first one is backbone network of the improved YOLO model. Backbone network of the improved YOLO model. So your backbone is the part that reads the image and extract the important details of the image. So backbone is nothing but that reads the image and extract the important details in the image. So this diagram show how the image passes through several blocks. So this diagram show how the images pass from several blocks. So first block is a convolution block. Convolution block. So these blocks are small blocks that pick basic details from the image. So convolution blocks pick the basic details from the image. Now coming to faster CTF block. So faster CTF block it is used it is nothing but the faster version of the CTF block used in YOLO object detection models. Uh, it can detect complex shapes like parts of the object, nothing but face, wheels, hands, etc. Now coming to uh, simplified SPPF. Now coming to simplified SPPF. So SPPF is nothing but spatial pyramid pooling fast. So SIM SPPF means simplified pyramid pooling fast. So it is the final layer on the backbone. It collect information from different scales. Nothing but information from small scale object, information from medium objects, and information from the large objects. So you collect the information from small objects, medium objects, and the large objects, and it helps the model to understand the object of any size. So nothing but this block gather all details together before sending them. Before sending them. So overall explanation is nothing but the image enters the backbone. It passes through convolution layers, and then it passes through faster CTF layer, and finally through simplified SPPF layer, which combines everything. Now, second one, overall architecture of the improved object detection model. So here we find a backbone, head, neck. So this backbone studies the pictures and picks the important details of the image. So simply it looks at the input image. The backbone looks at the input image and process three levels of features. Nothing but small features, medium features, and large features. So small features are nothing but tiny details of the image. Medium features are nothing but medium-sized details of the uh, objects. Large features means whole objects, nothing but complete objects. So these features from three arrows. So these are the three arrows. Now coming to head, it consists of path aggregation network and cross-scale feature path aggregation network. So this head receive all the details from the backbone. Then it mixes the information together so the model can understand the image better. So it can head containing PANET and path aggregation network and cross-scale feature path aggregation network. So these two models combines the small and big details of the image, and so the model can see the full picture, complete picture clearly. Uh, so by mixing all the levels of information, the model can easily detect small objects, medium objects, and big objects. Now coming to third one, neck. Nothing but it detect the layers. It detect the layers. Uh, so here these are the final object detection. So these arrows, each arrow is coming to produce a detection object. So each arrow coming in produce a detection object. So one detection object for one detection output is for small object, and second detection output is for medium object, and third detection output is for large objects. So detecting output of small objects, detecting output of medium objects, and last one detecting output of large objects. So these green boxes, nothing but detection, all the final layers are the final layers that predict bounding boxes, nothing but a box around the object. Next, object class, nothing but name of the object, and confidence scores, confidence score, nothing but how sure the model is about its prediction or how confident the model is. So simply backbone is nothing but it extract the features, head consisting of path aggregation network and CCF panet. It combine the features, and third one neck, nothing but it output the object predictions. So backbone extract the features, head combine the features, and the neck output the object predictions. Now coming to third one, structure of reparameterization fast plot. So rep indicates reparameterization. Reparameterization nothing but combining many layers into one layer. Combining many layers into one layer. So structure of reparameterization fast plot. So reparameterization is nothing but combine many layers into one simple layer after training. And faster means faster computation. So, so here it has two sides, left side and right side. Left side is nothing but training time, nothing but complex structure, and right side is nothing but inference time, nothing but simple structure. So left side is training time, uh, nothing but complex structure, and the right side is inference time, nothing but simple structure. So, this is the during training, left side is a training stage. Left side is nothing but the training stage. Um it has multiple parts. It has multiple paths. So 3x3 convolution layer, 1x1 convolution layer, and partial convolution, and CA block, nothing but coordinate attention block, coordinate attention block. So 3x3 convolution layer is nothing but a window that looks 9 pixels. The window that looks 9 pixels at a time in the image. The window that looks 9 pixels at a time in the image. So one into one convolution block means the window that looks only one pixel. The window that looks only one pixel at a time. So 3 into 3 convolution block means the window that looks 9 pixels at a time in the image, and 1 into 1 convolution block means the window that looks only 1 pixel at a time. Now coming to partial convolution, it is nothing but to process the important parts of the image. Partial convolution process only the important parts of the image. Now coming to CA block. CA means coordinate attention block. Coordinate attention block. Coordinate attention block, nothing but it helps the model to focus on important parts of the image. Now coming to two 1 into 1 convolution blocks. So these two 1 into 1 convolution blocks which are at the end will clean, adjust and mix the final information. So the two 1 into 1 convolution blocks which are at the end. So the two 1 into 1 convolution blocks which are at the end will clean, adjust and mix the final information. So cleaning means removing unusual information. Cleaning the information is nothing but removing useless information. Removing useless information. And adjusting final information is nothing but changing the data. Correcting the data, changing the data. Now mixing the information is nothing but combining the features together. Combining the features together. Now coming to inference, particular inference. So after training is finished, these complex paths are merged into one simple path. So right side inference stage. So it has a 3 into 3 convolution block, one CA attention module, and two 1 into 1 convolution blocks. So in simple works, the big and complex training block, is collapsed into smaller block that works faster. So in left side, we are finding many layers. That means the model is at a training stage. And in right side, we find many few layers. Nothing but it is in inference stage. So running stage means the model learning better. Inference stage is nothing but the model runs faster. So this rep faster block is designed to be smart while training and fast while running. So it is smart while training and fast while running. Now, next coming to structure of simplified SPPF. SPPF is nothing but spatial pyramid pooling fast. So SPPF is a small block inside the YOLO detection model that help the model to see objects at different sizes. So it is a lighter and faster version of SPPF module used in YOLO model. So this simplified SPPF is a block inside the backbone that collects information from the image at multiple scales, nothing but small, medium objects, medium objects, and large scale objects. So first one, yellow box, first convolution. So it is a smaller layer that prepares the input. Small layer that prepares the input. Nothing but it cleans and arrange the information. Nothing but it cleans and arrange the information. Now, second one, simple attention module. Simple attention module. SIM-AM is nothing but simple attention module. So it helps the neural network to decide which pixels are important. So this helps the neural network to decide which pixels are important. Now coming to orange boxes. So max pool 2D boxes. So this max pool 2D looks at the small block of the image, like 2 into 3, nothing but looking 4 pixels at a time, or 3 into 3 convolution block, nothing but looking 9 pixels at a time, and picks the largest value, nothing but most important part of the image. So it is used to reduce the size of the image, to keep the important information, and to make the module faster. So this max pool 2D is used to reduce the size of the image. It keeps the important information, to keep the important information, and to make the module faster. So in this image, you're finding three max pool 2D boxes for pooling again and again, again and again. So it simply, this max pool 2D simply reduce the image slowly and keep the maximum values. It's reduce the image slowly and keep only the maximum values. Now we are finding here adaptive average pool 2D. Adaptive average pool 2D. So it divides the image into small boxes. It divides the image into small boxes and take the average value of each part. It divides the image into small boxes and take the average value of each part. Now here we are finding adaptive max pool 2D. It reduces the image and take the maximum value from each part. It reduces the image and takes the maximum value from each part. This one, it takes the average value of each part. And this one, it takes the maximum value of each part. Now coming to concat. Nothing but it put all features together in one place. So it takes the, concat take the output of max pool, and output of adaptive average, and output of adaptive average pool query, and also the output of adaptive max pool query, and combine them to get a single output. So this structure combine all the features together in one place. So here you're finding the final convolution layer. It cleans and mixes the combined features. It cleans and mixes the combined features. Cleans the information is nothing but removing unwanted information. So cleaning is nothing but removing the unwanted or noisy information. Mixes means combining useful details in a better way. Combining useful details in a better way. So overall, simplified SPPF gather small, medium, and big features and mixes them together to help the model detect objects of all sizes. Now coming to this diagram. Uh, so here PS convolution block, PS bottleneck, and CPSC1, CPSC2, and CPSC3. So first one, C1 means partial convolution. Partial convolution. It process only the important parts of the image. It process only the important parts of the image. So see here, convolution, nothing but normal convolution. This one is partial convolution and this one is normal convolution. Uh, Next one is DW convolution, nothing but depth-wise convolution. Depth-wise convolution. So it looks each layer separately and it looks each layer separately. So this depth-wise convolution looks each layer separately. So it is very fast. Whereas the convolution looks everything in the image and find more details. This partial convolution looks important parts of the image, and normal convolution looks complete details of the image, and depth-wise convolution looks each layer separately, and so it is very fast. Next one, concat, nothing but putting all the results together. So join the outputs of partial convolution, normal convolution, and depth-wise convolution, and collect the information and combine them together. Next, coming to shuffle, nothing but it makes the layers of information in the image, mixing the channels, nothing but mixing the layers of image in the layers of information of the image. So here we're finding add, nothing but connection. Say add is the original old information. Add is the old information. So it nothing get lost here. So add is nothing but the original input to the final output. So add is the original input to the final output. It keeps the important information safe. It keeps the important information safe. Now second one, partial shift bottleneck. Partial shift bottleneck. Uh, so it is a small box made by using PSC, nothing but partial shift convolution. Partial shift convolution. So this PS bottleneck, nothing but partial shift bottleneck, uses the partial convolution and also the partial shift instead of full convolution. Instead of full convolution. Here you're finding CPSC1, CPSC2, and CPSC3. Uh, so this one, CPSC1 is the uh, smallest version. So the CPSC1 is the smallest version, and CPSC2 is a better quality than CPSC1, but it is fast. Now, third one is CPSC3. Nothing but is the largest version when compared to CPSC1 and CPSC2. It has more layers. It has more layers. So it has many features than CPSC1 and CPSC2, but it contains more calculation, nothing but computation. So the CPSC1, CPSC2, CPSC3 are nothing but small, medium, and big version made by partially shifted bottleneck. And this partial shift bottleneck is nothing but a small block made by using partial shift convolution to improve the features. And this partial shift convolution is nothing but a fast and cheap way to get the features. Now coming to enhanced path aggregation network. So enhanced PANET is nothing but improved version of PANET that mixes the features even better. So the model can detect objects more accurately and faster. So see here we are finding upsample. Upsampling is nothing but increasing the size. Upsample is nothing but increasing the size. So it makes the image features bigger. So it makes the image features bigger and help to detect the small objects. Upsample is nothing but increasing the size. It makes the image features bigger and help to detect the smaller objects. Now, concat is nothing but combine the features of the image, nothing but parts of the image from medium, small, medium, large scale objects information. CTF. CTF is nothing but cross stage convolution fusion. Cross stage convolution fusion. So CTF is a block that split the features, nothing but useful things of the image, process them and joins them again to make the features better. And we are finding here CSP1, CSP2, CSP3. So CSP means cross-stage partial block. Cross-stage partial block. So the CSP improves the mixed features, so detection becomes more accurate. So CSP1 means small CSP block. CSP2 means medium CSP block. And CSP3 means large CSP block. So CSP1 means small CSP block. CSP2 means medium CSP block. And CSP3 means large CSP block. So these blocks clean and improve the mixed features. So here you are finding three outputs. Top output is for large objects, and medium output is for medium objects, and the bottom output is for small objects. So this is output is for large objects, this output is for medium objects, and this output is for small objects. Now coming to cross-scale feature fusion PANET. So here we're finding this normal convolution. Next we are finding the upsampling, nothing but increasing the size of the image, and CTF, block that if you split the features, and concat, nothing but combine the parts of the image. So upsample means making features bigger, convolution and CTF clean and improve the features. Concat means combining features on different levels, and output means three feature maps for detecting small object, medium object, and a large object. So these are three outputs. These are the three outputs. So output for a large object, output of medium object, and output of small objects. So concat means combine the features from small object, medium object, and large objects. Convolution and CTF means clean and improve the features of the image. Upscaling means nothing but making the features bigger. So these are the models used in this paper. So these are the models used in our paper and real-time object detection based on YOLOv8. So these are the models used in our paper, namely improved version of real-time object detection based on YOLOv8.